So kinetic energy is the energy which is moving along the work done, and potential energy is the energy which is stored before the work is done. Cos differentiation of cos theta is minus sin theta. Negative of, you have to change the form to sin theta. Final expression is always about the energy, the total energy. That means you have to sum up kinetic energy and potential energy. You have to fuse it together. Hello everyone, I am Vrinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to session 2 of chapter 14, and chapter name is Oscillations. So, in our previous sessions, we had studied regarding some introductory part of the oscillations, and again we are going to study just some terms to know, and after which we will be proceeding with the energy of the particle which executes SHM, as well as the oscillations which is undergone by the spring. Okay, so now let us introduce certain terms, and the terms can be period, which is also called as time period, which is given by T, frequency, which is given by nu, amplitude, which is given by lambda, and phase, which is given in this. Okay, so here we have time period, frequency, amplitude and phase. So we have got a graphical representation, displacement as a function of time over here. So since this is origin, we have a wave structure in this way. So this part is said to be two crests, and this part is said to be two troughs. Okay, so this is trough and this is crest, and the distance between them is known as wavelength, and that is lambda. So this part, there will be the phase which is determined, which tells that it is the time taken by a wave to complete one circle, which is also called as the time period, which is given by T. One circle in the sense it's a one cycle. Okay, so that is all about period, T. And we have frequency. Frequency means how many number of lines. We'll say that the frequency is more. If the frequency width is very high, we will tell the frequency is very less over there. So the period and frequency is done, and other one is amplitude. What is the amplitude? Amplitude is nothing but the height of the wave, to which height it goes. So this can be the amplitude. And lastly, it is about the phase. It's like phase is nothing but the exact time taken by the wave to complete one complete cycle, and after one cycle again it starts from the cycle wherever it has stopped, and from there we continue the phase. Okay, so that's all about these terms to know, which we have discussed in the previous session. So now let us move to the energy of the particle which executes simple harmonic motion. So what is that simple harmonic motion? It is the motion which a particle executes wherein it has got constant frequency and constant amplitude. The frequency and amplitude doesn't change. Such kind of a motion is known as simple harmonic motion. This is executed by a particle, and let us check the energy of the same particle which executes simple harmonic motion. Okay, so now we have energy in simple harmonic motion. Okay, so what is that energy? It is the capacity to do work. Do work. What is doing work over here? That is the particle which executes SHM. Okay, so here we consider the total energy of the particle, which can be calculated as kinetic energy plus potential energy. Okay, so kinetic energy is the energy which is moving along the work done, and potential energy is the energy which is stored before the work is done. So that, suppose if you consider a spring over here, a spring which is in a mean position. So if this is a mean position, at mean position the kinetic energy is said to be 0 and the velocity is 0, but the potential energy is maximum. And when it starts oscillating, there is velocity and there is kinetic energy, because I told you the kinetic energy is the one which acts along the work is done. So kinetic energy is maximum, velocity is maximum. At that moment the potential energy will be 0. It's a vice versa. Okay, so after this what we have? We know that angular velocity omega is equal to 2 pi by t, and velocity is nothing but change in displacement by time taken, wherein we know that y is the displacement of this particle, so it can be a sine omega t as we know. Okay, so these are the known terms. So let us check the velocity, okay, because in order to calculate kinetic energy, we have the equation half m and v square, and here v, what is v? That is the one which is given there. So v is nothing but the differentiation. V is equal to d by dt, and what is with the d? It is y, and what is the value of y? A sine omega t. So here we undergo differentiation. So how was the differentiation taken place? We are differentiating one equation with respect to dt. So if this is t, something with that t itself has to be differentiated. So what is there with t? That is sine omega t. Okay. So this part has to be differentiated. So what are we supposed to do? We have to write a because it is along with sine t itself. So we can write this a as it is, and sine omega t changes because since t is associated with sine and omega, the sine t has to be differentiated. Differentiated means it has to change its form. Okay. So sine omega t becomes cos omega t because differentiation of sine theta is nothing but cos theta. In the place of theta we have omega t. So differentiating sine omega t becomes cos omega t. Okay, so cos omega t, and it is like a chain form of a differentiation. We took a and we took sine omega t on the whole. Okay, so after differentiating sine, what are we left with? It is omega and t. So differentiation of omega and t is nothing but just omega. T is considered to be only 1. Okay, so that is the thing, t is 1. The value of t will be 1 because we are differentiating t with respect to dt. So when that is the thing, we are not considering t again. Okay. So what is with t? It is just omega. So write only omega. So what are we left with? A omega cos omega t. Okay, if you just know the basic formula of differentiation and integration, it is very, very easy for you to calculate these things. So we are left with a omega cos omega t. So now what we have? So this will be the velocity. V is equal to a omega cos omega t. Okay. So now we know that the kinetic energy is given by, kinetic energy is equal to half mv square. And here we can write half m. What is v? It is a omega cos omega t the whole square. So it can be written as half, and it is written as m a square omega square and cos square omega t. So according to trigonometric formula, cos square theta can be written as 1 minus sine square theta. That is the formula. Okay. So this can be written as m a square omega square by 2 and 1 minus sine square. In the place of theta we have omega t. Okay. So now again you will have to fuse each and everything. So it becomes m a square omega square minus m a square omega square sine square omega t. So you have m as a constant, just take it out. M and omega square, you will have to retain it outside itself, and you have to take only a square. So you will have kinetic energy is equal to m omega square into a square minus a square sine square omega t. So we are left with divided by 2. So here we have m omega square divided by 2 and a square sine square omega t is nothing but y is equal to a sine omega t. It is a displacement equation, this part. So square the displacement equation and you will get the answer. M omega square divided by 2 into a square minus y square will be the kinetic energy equation. So this will be the equation for kinetic energy. So there are two cases, at mean position and at extreme position. So at mean position, the value of y is said to be 0. So what happens to the kinetic energy? It becomes m omega square divided by 2 into a square. So this will be the value of kinetic energy because y is said to be 0. And the case 2 is at extreme position. We don't have any kinetic energy because there will be y will be is equal to the amplitude, that is the amplitude of the oscillations will be too high. So at this position our kinetic energy will become 0. That is because y is replaced by a, wherein this a and a gets cancelled, so it becomes 0. 0 into something is always 0, so kinetic energy is 0. So that is all about the kinetic energy equation. That is, the particle executing SHM has got certain kinetic energy which is equated in this form. So now we have got potential energy. So let us check the acceleration of the particle in order to find out the potential energy. So acceleration is given as dv by dt. Okay, so which can be written as d by dt of what is v? V is nothing but a omega cos omega t, which can be equated as a is equal to, with respect to t we are differentiating, so a remains there, omega and cos omega t has to get differentiated. So cos, differentiation of cos theta is minus sin theta. Negative of, you have to change the form to sin theta. So it is minus over here into sine, in the place of theta we have omega t, and differentiating only this now, that is omega t, we have omega with us. So what remains? A is equal to, that is small letter a is equal to minus capital letter A omega square sine omega t. So that will be the acceleration. And now we have got, according to Newton's second law of motion, mass into acceleration. And what is mass? That is retained as it is, and a acceleration is kept as a omega square sine omega t. Okay, so when this is a condition, just take m into omega square the outside, and what are we left with? A sine omega t. So what is a sine omega t? That is nothing but the displacement y, which can be given as y. So F is equal to m omega square, and y is the force equation whatever we are having. So the change in work done, so it can be given as dw is equal to force into the displacement. Work done is nothing but the force into displacement. So it can be given as dw is equal to, what is force? It is negative. Why negative? Because it's a restoring force, and always we have negative over here, that negative will be placed here. So minus m omega square into y into dy. So this is the equation, wherein your minus means it is nothing but the restoring force. So we just calculate for the force over here, minus you will leave as it is. So for the total work done by the system, what are we doing? It is like integrating dw, which is equal to integration of m omega square y into dy. From where to where? From 0 to the displacement y, because it's undergoing certain displacement. Okay, so here we have displacement is determined by y, and time taken from 0 to y, what is the displacement? Okay, the amplitude. Okay, now we have integrating of dw will be the total work done, which is given by capital letter W, which is equal to integrating m omega square and y into dy, wherein m omega square is taken as constant and it is taken outside. So I'll just take m and omega square angular velocity to be constant, and we have integration of 0 to y and changing dy into dy. This will be the integrating concept. So W is equal to m omega square y, that is x into dx formula, or y into dy formula is squaring that. That is, I told you, it is always x to the power of something, whatever is there, something you have to add with that plus 1. So here we have y to the power of 1 is there, which is not written over there, y to the power of 1, which means y to the power of 1 plus you have to add to the power, you have to add 1 and take the same power to the denominator. So what it becomes, y to the power of 1 plus 1 is y square. So it becomes y square divided by the same 2 is taken to the denominator, wherein it varies from 0 to y, and we have our integrated part. So what happens to this? W is equal to m omega square, head to toe method we have to see. So y square, in the place of y we have to put the same thing. Since it is the same alphabetical term, there is no difference in that. So this is nothing but 0, which is for the previous step. Don't get confused with it. So we have got our y m omega square, and instead of this y we are replacing this y. So since it's the same alphabet, it's not necessary that you have to change again and again. So y square, and we have divide by 2, wherein again you will have minus y square. Instead of y it is 0, so since it is 0 divided by 2, it gets cancelled, okay, which is not valid. So we have m omega square y square divided by 2. So we can write this as W is equal to half m omega square and y square. So this will be the equation for potential energy. Now what are we supposed to do? The final expression is always about the energy, the total energy. That means you have to sum up kinetic energy and potential energy. You have to fuse it together. So now let us do the fusing of kinetic and potential energy. So we know that energy is equal to kinetic energy plus potential energy. So what is your kinetic energy? So it is nothing but half m omega square a square minus y square plus half m omega square y square. So this is the equation of kinetic energy as well as potential energy. So now how to equate this? Now we have total energy E is equal to, take half outside and m omega square as a common out. So what are we left with? We are left out with the first equation, it will be a square minus y square, and in the second equation it is just plus y square. Okay, so what are the things which are common and with a different sign? It is y square, which cancels out. So we have total energy is half m omega square and a square. So this will be the total energy of the particle. You can just write it here. Therefore, the total energy of the particle executing simple harmonic motion is given by this equation. That's all about this energy of the particle which undergoes simple harmonic motion. So now let us move to this expression for an oscillations due to spring. So what do we have here? Here we are supposed to consider a spring which is fixed at one end. So we have just the spring which is fixed, and there is a load what is here, and it is stretched and it is restored back. So the stretching and restoring back we have already discussed in the rest of the classes. So that is from this is the mean position, so it undergoes displacement and it gets restored back, which is given by stress is proportional to strain, and F is equal to minus Ky, because minus is nothing but the restoring force sign. So according to this, we have acceleration formula to be minus omega square y in case of simple harmonic motion condition of a particle. So now equating this to Newton's second law of motion equation, and it is nothing but F is equal to m into a, the product of mass and acceleration. So in terms of a, if you just substitute this, we have F is equal to minus m omega square y. So we equate equation 1 and equation 2, and that can be equated as minus m omega square y is equal to minus ky, wherein your y and negative and y gets cancelled. So m omega square is equal to k. So Omega, if you just retain it, omega square is k divided by m, which can be written as just omega, wherein root is taken to the other side, k by m. So this will be the angular velocity. So now what are we supposed to do? We have angular velocity. In order to find the oscillations of the spring, what are we supposed to do? We have to take time period relation. So the one which equates time period and angular velocity is the formula omega is equal to 2 pi divided by t. So t becomes 2 pi by omega. Okay, so when we have this, how are we supposed to calculate? That is, t is equal to 2 pi divided by root of k by m. So when it is taken towards up, it becomes 2 pi into root of m by k. And we know that the frequency is always the inverse of the time period. So frequency is given by nu, which is equal to inverse of time period t, which can be given as 1 divided by 2 pi into root of k by m. So this will be the final equation of the frequency, and this is all about the time period. So in order to identify these oscillations of the spring, we have got the time period as well as frequency equation. So this is all about the expression of the spring which oscillates. So in today's class, we have discussed about certain terms to know under oscillations, as well as we have studied the two expressions, which one is with the energy which executes SHM, energy of a particle that executing SHM, and the other one is nothing but the oscillations of the spring. For that, we have derived an expression, that is the expression for time period. So out of this, in this session, whatever I have done, the expression in order to get the oscillations of the time period acts as an important concept here. So I want you to concentrate on this part, as well as let us all introduce that the oscillations of the simple pendulum in the next session. Until then, all of you have a good day. Thank you.